Hello Trig, welcome back. This week we are going to be doing even more with Radians. We are going to be focused on the graphing of Radians, so graphing the parent functions, graphing some transformed functions, and even writing the equations of those transformed functions. Alright, so let's get started. First, we want to think about graphing the parent functions and thinking about how we can do that in Radians. Again, like always, you are more comfortable for right now in degrees, and so I can encourage you to the best of my ability to try to get more comfortable in Radians. So please, with me right now during this video, try to stay with your mindset in Radians. Rather than thinking about let's go into degrees, then convert to Radians, then think about it that way. Let's try to leave our mindset in Radians as much as possible. So whenever we're talking about the sine function, we are thinking about the vertical position on the unit circle. So there are 5 key points that I want to think about. Here is my first, here's the second, here's the third, here's the fourth, and then back around here's the 5th key point that I want to think about. What is the vertical position? What is the radian value that I'm at when I'm at that position so that I can come up with a good parent function sketch. So for that first one, I'm seated right here on the positive x-axis. My vertical position is 0. My output is 0. The input also, in this case, is 0. I've got 0 radians, so I've got 0, 0, my beautiful anchor point that I've always got for my sine function. Then from here, the next value that I've got, here at the top, position 2, here I've got a vertical position of 1, and I'm seated all the way up at the top. We know that the entire half circle over here is pi, which means up here, this splits it in half as exactly pi halves radians. Let's just see, let's go out, I don't know, 1, 2, 3. Yeah, he'll be pi halves radians. And then we're gonna go up and we'll let 1 be, that's a half, that'll be 1 for us. Stretch it out because we can. Okay, then if we keep going, here at my third position, we now are back to having a vertical position of 0. We're seated on that x-axis. And here we know that we are half a circle away, which means we are at exactly pi radians. So if I go another 1, 2, 3, 4, here is pi radians. We're seated back at a vertical position of 0. Continuing on down to the bottom position right here. At that 4th position, I've now gone a full half circle and then another quarter of a circle, so I'm now all the way down at the bottom at 3 pi halves, or 3 pi halves. And while I'm here, I now have a vertical position of -1. So 1, 2, 3, 4, at 3 pi halves. I should be at -1/2, -1, way down here. I'll represent -1 for us. And then finally working our way all the way back around to where we started, same place right here. I'm back at 2 pi because I've made one complete full circle around 2 pi and my vertical position is back at 0. So my full parent function looks exactly like it did in degrees, but now my units have switched, so where those important points happen is now in terms of radians. Great. Same thing with cosine. This time when we're dealing with cosine, we want to be thinking about the horizontal position at all costs. We're going to continue with those same important key points. So my first one is seated right here. Here I'm at 0 radians. I've not yet moved in any way or got around that unit circle in any way. My horizontal position from that y-axis is at a positive full 1 here. Half 1 will be way up here. So I've got my first point right there. Next, I'm going to rotate a quarter turn around that circle, a quarter of that 2 pi or pi halves. And when I'm there, my horizontal position away from the y-axis, well, I'm seated on the y-axis, so it is 0. Continuing around, doing 1/2 rotation, or pi radians away, I'm now at a horizontal position from the y-axis of -1, so here is pi, and I should be down at -1. Continuing around, get to a 3/4 turn, 3/4 of that 2 pi, or 3 pi halves. Here my horizontal position is back to 0. I'm seated on that y-axis. And finally, whipping all the way back around, I've done one complete full rotation, so I'm all the way out at 2 pi. And again, my horizontal position has gone back up to 1. So my parent function for my cosine graph looks similarly to how it did for my sine graph as well. Should look the exact same as the cosine graph that we've seen before in degrees. However, the units on it have changed just slightly. If we notice now, in both cases, the period of our parent function is 2 pi. Same here. Our period is 2 pi. Because that is one complete circle or one full rotation around that unit circle. Okay, so that's helpful and useful for us because when we get into later graphs, we'll see some transformed things. We'll want to remind ourselves what the parent functions look like. But my first question is, we already know how to write all of these transformed functions. We've done it all. We did it all in degrees. So really, what I want to know is, what's even new when we change to being in radians? And the answer is not everything. Our input changed, which from being in degrees to being in radians, which means anything that had dealt with the input before, transformations that deal in the horizontal direction, things that affect the x, any of those kinds of phrases, our way of thinking about those might have to change slightly, but anything that was dealing with our vertical transformations, our output hasn't changed in any way. Our output is still between -1 and +1, still talking about either that horizontal or that vertical position, depending on which trig function we're talking about. And so nothing about our vertical transformations has to change. So really, we only have to narrow it down to the two cases of those horizontal transformations. So the first that we're going to think about is, let's just jump right into horizontal translations. We're going to assume that we're dealing with a parent function of y is equal to sine x. Here's what that graph is going to look like. This, remember, is a transformed this is a transformed sine function here. What we notice is that the anchor point is now here at -pi halves, 0. So that means that my graph was translated to the left by pi halves units. And these translations, while they look a little bit differently because now all of a sudden there is a pi involved in them, and this technically is then in terms of radians, these translations really don't do much to change how our equation was written from before. We are going to continue to think about this as, how do I go from this point back to where I should be on the parent function? How do I do that maneuver right there? And what I would tell you is you would take your x value and you would have to add that pi halves back in order to be where the parent function is. And there's our equation. It looks really similar to how it did when we were in degrees. However, when we were in degrees, that pi halves probably said something like 30, 60, 45, 90, one of those more comfortable degree values. Now it's going to be one of our more comfortable radian values. All right, we also have horizontal dilations. Now, horizontal dilations, we've always had two ways to think about it. We're going to continue to have two different ways to think about it, and I want to make sure to go through both. So in this one, we're going to assume that our parent function is a cosine function. Here's what our graph looks like. What we notice right off the bat is that there is one full period that shows up over the course of pi. Here it is right there. Which means that our graph was horizontally dilated by something in some capacity. What exactly it was dilated by, remember we have two ways of thinking about this. The first realm that we can live in is the frequency realm, which is how many child periods fit in the parent period. So we know that the parent period in this case is 2 pi. That's something we already knew. So in this distance right here, 0, 2 pi, oops, right there. 0 to 2 pi right there. How many child periods do we get to see? Well, let's see. We get 1, 2 full periods that fit into there. So our frequency in this case is equal to 2. which tells me exactly what I dilated by, which tells me that my equation is y is equal to cosine of 2x. There's also the other realm that we can think about that is more along the lines of dilations and multiplications. So we're going to think about that point that's right here that is at pi comma positive 1. This one's kind of dilation land. I don't know what better title is for it. Dilation land. We know that we want this point originally. This point was at 2 pi comma 1. So we need to, similarly as what we did in our translation land, what we want to think about is what do I need to multiply this pi by in order to put it back where it's supposed to be, all the way out there at 2 pi. Remember, this time I'm multiplying because I'm dealing with dilations. In the previous slide, I was adding and subtracting because I was dealing with translations. But what do I need to multiply by? Well, that thing that I need to multiply by is also 2, which tells me again that my equation is cosine of 2x. You can think about it in either of these two methods. Either are fine. Some are more helpful in others. In some situations, some are more helpful in others. Either way, we find that our dilation is the same. It is a dilation factor of 2 via the frequency. But now, here's a warning and a side note. Our dilation factors and horizontal dilations can get weird when we're in radians. They could already get weird when we are in degrees. If I all of a sudden said that I wanted to have a sine function that had a period of, 52 degrees, yeah, I was going to get a weird dilation factor. But it was always just involving numbers. And so then it was like, okay, well, what 52 times what is going to give me 360? And I could figure it out there. It's not really all that different to do it when we're in terms of radians, although we might have extra pi's showing up in our equation. So I want to just walk through one really quick. So let's say, for example, we want a graph to represent the cyclical nature of the moon phases. So it's going to look like this. It's going to have a period of 28 days or 4 weeks. So it's got a period of 28 days, 4 weeks from new moon to new moon. Just like that. So now, if we were trying to write this equation in radians, the thing that's going on here is we have to figure out, well, this has to jump back, this point right here that's at 28 comma positive 1 has to jump back to being at 2 pi comma positive 1. Or we need to think about, okay, well, where is 2 pi? 2 pi, well, pi is like 3.14, so 2 pi is like 6.28, blah, blah, blah. So, okay, great. Right here-ish, guesstimating, of course, just a guess. Right there-ish is about 1 period. So how many of my full cycles fit into that period? Good question. Good question, Ms. Glenn. So we don't really want to think about this one in our frequency land. Thinking about this in our dilation kind of a land, however, we can continue with this idea. We want to put that 28 back to being 2 pi. So 28 times something gave us 2 pi from before. So then that's something that I'm solving for. I'm going to isolate it. Question mark is equal to 2 pi divided by 28, which is pi over 14. So because there's no other transformations that are going on here, this is a fairly benign thing to do. And in the end, I'm left with y is equal to cosine of pi over 14x. The end. However, in other situations, when you've got horizontal translations and horizontal dilations involved, it's possible that you start to get lots and lots of pi's involved. Like something like this. I'm just going to make one up. I don't know. You dilated by pi halves and you translated by 5 pi sixths. Starts to get a little bit messier as far as what all goes into that equation. So they can get a little bit weird, and yes, pi can absolutely show up as a dilation factor. Okay, continuing on, I'm going to ask you right now, pause the video, try to fill this out yourself, identifying all the features, writing the equations yourself. Then you can unpause and I will talk through it. So pause that now. All All right, now that you've paused, let's check in, let's talk about it. What are the things that we notice right away? Here is my midline at y is equal to +1. I noticed that from there that my maximum value occurs at +4, which means that my amplitude is 3. I also noticed that neither of these are perfect, aren't they? This is going to be 3 pi halves. So what's halfway between those two things? Nope. 7 pi fourths. 7 pi fourths here. Because that's 6 pi fourths, 5 pi fourths, 4 pi fourths. Yep, okay. Negative 7 pi fourths. All the way to here, which is then going to be, this is 8 pi fourths, so this will be 9 pi fourths. I noticed that there is 1, 2, 3, 4 things before each pi, which means each of those lines represents pi fourths, so I'm splitting them up and figuring them out that way. And then I noticed that if I'm going to represent this as a sine equation, here's where I start. The next period starts at that next blue dot along the midline. So I'm trying to figure out what is that distance. So from negative 7 pi fourths all the way out to positive 9 pi fourths is a total of 16 pi fourths, or 4 pi. Came from 16 pi fourths. The x-coordinate of the anchor point, oh, I guess I should have split that up for sine and cosine. The x-coordinate of the anchor point for my sine function here would be then at negative 7 pi fourths. You could have also put it at 9 pi fourths, or any of the other options that are there with reflections or things like that. For cosine, we would put it at negative 3 pi fourths, or probably, let's see, what would that be? 13 pi fourths. And so now we have all of the information that we need to completely write our equation. All right, so if we're writing a sine equation, we know that our amplitude is 3. Then we've got sine. We know you have a period of 4 pi, which means that we have a frequency of 1/2 x, so let's see, plus 7 pi fourths. Or right here, you could say minus 9 pi fourths, either way. And then finally plus 1. For our cosine function, we still have an amplitude of 3. We still have the same period of 4 pi, so 1/2 is our frequency. It's either positive or plus 3 pi fourths, or it is negative 13 pi fourths plus 1. And there we go. All right, so that's how we can go from the graph is given and we're writing the equation. Those are things that we've done before, but how about we go the other way this time? Here's the equation. It's your turn to graph it. Pause the video, sketch this out on your paper. I suggest you use a similar scaling to your graph as me. Try it out. Do so now. All right, here's what we got. We know that we have a midline of y equals +1. We know that we have an amplitude of 2. I have a frequency of 3, which means I can fit 3 whole child periods in that one parent period, which means that I have 2 pi thirds. 2 pi divided into 3 equal pieces, that's now my period, so that way I can fit 3 whole child periods into that one parent period. And because I'm dealing with a sine function, x-coordinate of my anchor point, well, I guess it doesn't matter if it was sine or cosine, but I am dealing with a sine function, and the x-coordinate of my anchor point has been shifted in some way, so now it's going to exist here at pi. I don't know why I put a parenthesis. I'm not writing the whole anchor point. It exists at pi. Okay, which means the x-coordinate of my anchor point is here at pi. All the way at the end. Okay. We can think through this. We got this. No big deal. We can do this. If my x-coordinate of my anchor point is all the way out here at pi, I also have to think about where it is on my midline. So I'm going to erase and move back. But just so we know, we're dealing with an x-coordinate of the anchor point right here at that +pi. All right, let's put all the things on this graph that we know. We have a midline of y equals positive 1. We've got an amplitude of 2, which means that I can go 1, 2 above that midline, and I can go 1, 2 below that midline. So I'm just leaving these orange ones as like boundaries for me so I know where my maximum and minimum value will go. I've got an anchor point at pi because it's a sine function. That anchor point is going to go on the midline. And then I know that I have a frequency of 3 or a period of 2 pi thirds. Okay, so then I can go forwards or backwards by that 2 pi thirds, and I should be able to have reached another anchor point. So because I can't really go any further forwards, the only thing that I can do is go backwards. If I go backwards 1/3, 2/3 pi, there we go. I can continue in this fashion, 1/3, 2/3 pi, there we go. 1/3, 2/3 pi, there we go. If you accidentally put your x-coordinate of the anchor point at negative pi, you lucked out this time, but please, please, please be careful and think about which way that translation actually moves our graph. Remember, that part is going child back to the parent. It's happening inside of those parentheses. It's happening to x. Okay, we know all of that to be true for sure, and so now here's what we know. From one anchor point to the next, halfway between those two anchor points, we are also hitting our midline. Halfway between our anchor point and that first midline place, we are hitting our maximum value, so all the way up here. Halfway between that midline and that next anchor point, we are hitting our minimum value. And there is one full cycle. I'll sketch out the other two in case you were graphing either of those other two. There's a second full cycle. And a third full cycle. Just like that. Great. All right, last thing is your entrance ticket. Your job is to write the equation in radians of the transformed cosine function that is shown below. You're going to complete this on your own paper, take the picture, submit it just like you have been, and then you're also going to fill in your answer on Google Classroom. Do this part now.